All right, so we're going to refer to, as I said, our original sort of experiment from the first week of class. We would like to know what is the average height of the adult on this planet, and the issue is we know we can't physically measure every adult. That would be impossible. There's too many people, and so what we ask then is we say, okay, if we sample that population, if we just take a sample of it, if we say, let's take 1,000 adults, or let's take 10,000 adults, or let's take 1,000,000, whatever it is, and maybe we'll take a bunch of samples. Maybe we have a bunch of people go out and sample, and the big question remains is, what can we say about our sample? So perhaps a better way of phrasing that is in the following. Big question out there. So when we analyze a population, using a sample or samples, how confident are we that our, say, sample mean or variance, etc., are representative of the actual mean, variance, etc. So I hope you understand this question. If I want to understand, again, if I want to know the heights of every adult person on the planet, and I only sample 10,000 adults, I am going to have a sample mean. I'm going to have a sample variance. How confident am I that my 10,000 samples, and when I average them out and get a mean and a variance, how confident am I that my sample mean is representative? Is it actually close to the real mean? Now, it seems like a silly question because we know we can't actually get the true mean, but we do at least have mathematical ways of asking or sort of quantifying how confident we are that our sample mean or our sample variance or our sample standard deviation, for that, are giving us good information. So what we like to do then is, I guess this is a question here. So one idea is to estimate, mu and sigma using samples. So we're looking for ways of sort of quantifying these ideas. So, for example, we call X bar a point estimate, and let's explain why we do that. So, I guess I should be more specific. We call X bar a point estimate. So what does this mean? So let's remind you of some things. So the population mean is some number we're calling mu. the sample mean is X bar. And so the question is, what can we say about how far apart these two numbers are? So how do we measure how far apart two numbers are? How do we quantify it? We use their distance between the two numbers. And in mathematical terms, that is the absolute value. So in terms of the geometric way of saying this is we were looking at, say, a number line. So take a number line. So let's look at a number line. And what we're saying is we have the true mean or the population mean on the number line somewhere. And then some other number is X bar, the sample mean. So you might remember that we give names to some of these things. For example, we talk about intervals on the number line. So let's pick an arbitrary number. Take a point, let's say, call it A. So in this picture, what can we say about A? Well, we can say the distance between A and mu is less than the distance between, say, mu and X. So again, I know this is sometimes challenging, but let's try to put our mathematical brain on here. This distance right here, what's happening? This distance right here is defined as A minus mu. And then this distance from here to here is the distance X bar minus mu. So one of the things that you learn in a math class, usually this is done in algebra, is the following. And on the next page, and I'm not writing this down to scare you, but I'm writing it down because what we're getting into, this last topic, is what's called confidence intervals. And they're very important when you're analyzing data. And the thing is, understanding confidence intervals, in my opinion, relies heavily on your understanding of fundamental mathematical notation, which most of us aren't that good at understanding. And things like absolute values that you learn about in an algebra class and how to work with them are very important here. And it's helpful if you have that piece. So let's do a little bit of thinking of this from a mathematical perspective. So let X be an arbitrary number. I don't care what it is. So here's a little math review. All X satisfying, say, X minus 3 in absolute value is less than or equal to 10. there's two ways to think about this. Now, look, I just picked 3 and 10 out of my head. I'm not exactly interested at all about their specific values. But what I want you to know is I want you to be able to interpret what this means. That's what we want. What does this mean? Well, it means two things, or two equivalent things at minimum. It means algebraically the following. So algebraically, if I could spell. It means x minus 3 less than or equal to 10 and x minus 3 greater than equal to negative 10. And if I add 3 to all the pieces, it means this. So that's the algebraic definition. Or not algebraic definition, but algebraic sort of interpretation. Now, the geometric interpretation so I guess geometrically, if you want, if you draw a picture, this is all numbers within 10 units of 3. So if you draw a number line, if I draw a number line like this, and don't say, I don't remember number lines, because my kids in kindergarten, that's what they do. They do number lines right now. So you learned them at least in kindergarten. You should hear them numbskulls up there doing that. All right, so let's put the number 0 here for sort of good measure. And if this is the number 3, everything that is within 10 units of 3, okay. By the way, no one yelled at me over here, so I guess I'll have to come over here and do it myself. Guys are not paying attention already. What is 10 plus 3? It's 13. So what we're saying is, if you go 7 units over here, you're at 10. And if you go, excuse me, now I'm making mistakes. This is 13. And then if you go over here, it's -7. So if you look at the distance, if you count, and even though this is, this is actually not the scale, I feel bad, but the fact of the matter is, if you wanted to walk from here to here, it's 10. And if you wanted to walk from here to here, it's 10. So for example, the number 4 satisfies this, but the number 15 doesn't. Okay, so does anybody have a comment or a question? Water tastes good. Okay, so here we go. If I go to the next page, let's formulate this in terms of what we've been studying. So in terms of mu and x bar, for example. So here's a theoretical scenario. Let's be very careful here. Imagine we know the standard deviation and we know, or the variance or the standard deviation, because that's always. So let's assume that we have some sort of normal distribution. We think it's normal at least. And we have some actual mean. We don't know what it is, but we're trying to estimate it. And we have our normal curve. And so we know somewhere in here, we go and take our sample and we get our sample mean. We can't assume that our sample mean is going to equal mu, so we know that it's either to the left or to the right of mu. And so what we'd like to do is we'd like to say, okay, how do we quantify how close X bar is, the sample mean, how close it is to mu? So in words, we would say to analyze how close X bar estimates mu, what we might do is we might look at the distance, as I suggested, between X bar and mu. By the way, you guys, I hope we remember from our math days that this is the same thing as this. 5 minus 3 in absolute value is the same as 3 minus 5 in absolute value. Now, if we assume we have some sort of normal distribution, and then what we know is we have this real nice sort of symmetry around the mean, and we know that there's certain properties about the area. So imagine we want to know what is the chance that X's distance from mu sits in some region under the curve. All right, does anybody have a comment or a question about that? Now let's think about our problem. If we're computing X bar, then we know that we know the number in our sample. What else do we know? Well, we know the number in our sample. We also know that the area under this whole curve is equal to 1. So let's pick a number here. Let's call it, for lack of creative, let's call it A. So let's put this point right here. What could we call this point? Well, we know that the way I've drawn this red point, that it is some distance from mu. Remember, this horizontal line, let me be very clear here, because I don't know how much we're picking up. This is, you could think of this as the x-axis or the number line, right? So this mu, maybe it's 0, maybe it's 37, who knows what it is. But how I've drawn this, what's important to note is that the distance from u to here is the same as the distance from here to here. And how can we represent this point? What is it? Well, let's imagine that we wanted to have a certain property. Particularly, we want to talk about the area under the curve. So suppose, for the sake of argument, we want this particular area to be, we're asking, is that x bar, is that going to fall under the curve where the area is a certain value? In particular, let's suppose we want to know, or we want x bar well, maybe another way of thinking about this is, it's a bad way of saying we don't want anything. We're not going to force things to give us what we want, but we can sort of ask questions or phrase them excuse me, in a certain way. Okay, so let me maybe try to step back, because I don't want to lose you. And of course, you guys are probably all sleeping right now anyhow, or playing Xbox or whatever the hell it is you guys do.
I'm trying to focus, but my internet keeps cutting in and out.
That's all right. Blame the internet. I like it. All I hear upstairs is my kid in school, so what the hell? You're in a weird world, I'm in a weird world.
It's been pretty bad all weekend.
What's that?
It's been pretty bad all weekend.
Been bad?
Yeah.
That's actually funny, Ethan. By the way, Ethan, I got your email about the My Math Lab stuff. Yeah, no, you're fine, dude. Don't stress about that. I'm here for the people, Ethan. I'm here to help you guys. Okay, so here's what we're looking at. If we go to our table, our Z table, and we look at this sort of distribution, look, don't forget, the central limit theorem gives us information. It tells us that if we take a bunch of random samples of a large population, that these things become normally distributed. So, this assumption that we're thinking about the mean and all this stuff as a normal distribution is not completely outrageous. And so if we go to the back of the book and we looked at a Z table, or if we went on the internet and looked for a Z table, we can find this value right here that's going to give us certain things. In particular, suppose that we wanted the following. So suppose the area of the red was 0.95. So that is this is 0.95. What would be over here? What would this region be? Well, this region that I'll do and say orange, what is the area here? The area here would be, well, if the whole thing is 95, then what's left over is 0.05. And if you divide that by 2, that's 0.025. And then the remaining area over here is 0.025. So what is this number? We can call maybe this, well, that's a bad color. So what is this? Well, we could do some fancy, I don't want to say fancy because it's not fancy. If we did some algebra and we applied some of those theorems that we've sort of alluded to, and we do some math, what we can show is the following. So this interval, well, this interval right here is called a 95% confidence interval. So let me go back here, change this. I didn't want to write this. So we call this thing, this interval right here, this mu, and then we have a question mark here and here. So we call this a 95% confidence interval. So it's convention to denote this number as something. So here's the convention. So convention is to denote alpha by 0.95, and then alpha over 2 is 0.025. So this is, we're giving these numbers names. We're calling them alpha. Actually, I wrote that wrong. Excuse me. Sorry. No wonder I'm a numbskull. Call this 0.05. So what is alpha? Alpha is the remaining area. That's the area outside of the red region. So if it's 0.95 is the red region, then outside is outside is 0.05. And if you cut that in half, you get 0.025. Now, it turns out that that number, on the number line we were looking for, if you do some algebra, and if you think about the central limit theorem, we're not going to do it, show that that number we want is the following. It is mu plus something, which we're going to call z some alpha over 2 times this scary thing. Now, look, if we look at the number line, We have our mu. And then this number, the magic number we're looking for, we are going to denote it Z sub alpha over 2. I know that's scary. And then it's sigma over the square root of n. So if you add that, another way of thinking about this, and I understand that this is a little overwhelming. This distance is Z sub alpha over 2 times sigma over the square root of n. And of course, by symmetry, and I know, again, we're taking some liberties, but by symmetry, if you come over here, this is mu minus this number. Yikes. So what is this Z sub alpha over 2? So this is sort of the scary part. So let's, again, this is often more confusing than, I feel bad, but it is. So Z sub alpha over 2 is the number or the Z value that gives the desired area. So for example, if for alpha equal to 0.05, then 95%, Z sub alpha over 2 is equal to 1.96. So let's, again, why is this the case? Why is that sort of, what are we saying here? So this goes back to your Z table. What Z value is going to give you, 95% of the area. So let's go to the internet and we'll show you what I mean by this. See if I can get, where's the one we've been using? We had that one. I use the same one we've been using. Now I can't find the one we used a gazillion times. Okay, here we go. Here's where we can, here's one table. So I have this standard normal table, and what I'd like to do is I'd like to find the Z value that gives me what I'm looking for. So what do I mean what I'm looking for? I want to find the Z value so that only 0.05 is left. Now, if you look at this particular table says the Z value corresponds to how much area is to the left of Z. So for example, as you would expect, if Z is 0, then you get half, because half in half equals 1. The total area is 1. So what we want is we want to know, how do we get to have 0.05? So if we recognize what that is, that's we need 0.025 actually. So we have to use this sort of table. And if you come down here, this table's not helping us because it needs, so if you look at this table, you'll see this number 9750 is what we're looking for, and that is 1.96. So what gives us the area of 9750, or the opposite of 0.025? Well, it's right here. So it's also it's useful to check your math. If you take 0.025 and then you add 0.975, you'll get 1. So again, let me reiterate what we're doing. We're looking for the z value. We're looking for the z value that gives me all the area except 0.025. That's what I'm looking for. And so what z value gives me? What's all the area except for 0.025? Well, that's this. 1 minus 0.025 is 0.975. So that means the z I'm looking for is 1.96. So it's right here. Okay, so even if you don't quite get that, that's not the end of the world. But it helps if you do take the time to understand that. It helps with this scary notation. So here's another way you can sort of think about what I'm saying. So the key intervals are the following. So we're looking at x bar minus mu. What is the distance between the sample mean and the actual mean? And we want to know, when is that less than this creature? Which, of course, this is equivalent. If you rewrite this algebraically, this is the same as mu less than x bar plus z sub alpha over 2. And then x bar minus z sub alpha over 2. And this should be a less than. Now we have there's three standard intervals. There's a 90%, there's 95, and 99. So we have three options. Well, the first option is we use z alpha over 2 equal to, say, 1.65. This is a 90% confidence interval. Z alpha over 2 is 1.96. This is the one that we did, the specific one we just did. This is 95% confidence. Or last, Z alpha over 2 equals 2.58. And this is 99% confidence. So what this does is this gives us a way of quantifying how good we think our sample mean estimates the actual mean. This is a lot of scary math symbols. I get that. But again, this is merely a tool. This is one tool. We take a sample of a large population and we ask ourselves, how confident are we that our sample mean, for example, is indicative of the actual mean. So one of the questions that students will ask me, I don't get as many this semester because we're all virtual, but in the normal world, you guys would come to my office and say, how did this come from? Where does this come from? All this. Well, remember, this formula, this comes from, we had these two key formulas. We had z equals x minus mu over sigma, but then we also had, from the central limit theorem, of this z equals x bar minus mu divided by sigma n square root. So that's where these things come from. So there's a lot of heavy math theory behind all this. And it's very difficult. You know, how do you know, my job is to figure out how do I introduce this stuff so that you can do practical applications without scaring you with all the math. And we have to give you a little bit of math. And I also want to give you some of these scary pictures, but I don't think they're scary. Because they're, you know, what good is any of this if you can't gain some intuition for what we're trying to do? Now, of course, most of you will sit there right now and say, well, I'm confused. I don't know what's happening. He's just drawing crazy things and you're going to take a nap and throw your hands in the air. And I get that. This is challenging. And frankly, you just don't learn this in 15 minutes. You got to read the book and then you got to read it again. And you have to compare and contrast the book with what we're talking about here. You might need to do some internet searches. This is a process to learn. It ain't magic pill to learn. So let's just fire in an example real quick, because really we got to get our minds off the heaviness that we were doing. Does anybody have a question right now? By the way, there's nothing that says you have to use 90, 95, or 99% confidence intervals. I mean, you can use 93% if you want it. So it's completely, I don't know. It's up to you how if you want to think about it that way or not. Anyhow, let's do an example and we'll see how this goes. This is the kind of stuff that you'll be asked to do.
What does the confidence things have to do like with it then? Wouldn't you rather be like 100% confident or 99%?
Right, but okay, that's the point. But okay, so maybe when we do an example, it'll make a little more clear. We don't know, right? Don't forget, our job is to try to quantify things, right? We don't know even if we're quantifying something if it's useful. Do you understand what I mean? We don't know. Like, so the bigger question is. So here's another way to think about it, maybe, is with enough analysis, and if you take the higher courses, you see how this stuff goes on. But what we do is we start analyzing these things and we say, okay, if our sample size is this many, then we know that our sample is giving us good information, or it's indicative of what's really happening. There's all kind of, this is the whole, what we're doing now is we're giving you a glimpse into what we call parameter estimation. But really, this is a branch of math and statistics that you can take classes upon classes on. It's a super developed yet open area where, you know, we're just looking for any piece of information that we can gain, and we don't even know if the information's useful. So I think your point is, well, why would you not always just do 99, right? Because then you're more confident. But the problem is if the wider you go, the less likely you know how close it is. So because your interval you're testing or estimating is bigger. Do you understand what I'm saying? There's more, another way of saying it, there's more unlikeliness or more randomness that can occur in that way. Anyhow, let's do an example. Maybe that'll clarify your question. I don't know. If it doesn't, then of course you can.
I think to me, it's just, I'm thinking like 99% confidence means that, you know, you're pinpointing exactly what you're trying to talk about. You know what I mean? So I think I'm just kind of thinking about it like in an inverse kind of way.
Right. No, that's not wrong. And that's a good point. But think of it this way. If I go back to this picture, we're trying to ask ourselves, we have a sample mean. And what we're saying is, if we do 99% confident, well, then all we're really saying is that we're really confident that it's somewhere not in the tips, right? Do you understand what I'm saying? But if I squeeze this red area down, then what I'm doing is I'm losing confidence that it's in there because there's more chances it can be outside of it. So like you're suggesting, if you give a little in one direction, you're taking away in the other. So if you want a little bit of certainty, you're giving out something else, and vice versa. So when you use the word inverse, that's sort of a good way to think about it, because what you're doing is you're accepting one bit of information by giving up other information. And I don't know if that resonates or not, but again, let's do an example, and I don't know if it will make you feel better or worse. So let's do the following. So here we go. So typical sort of O'Grady example here. So we did something similar to this the other day, so we'll run it again. So a hospital collects data and finds the ER averages, I don't know, how about say how about 22 patients an hour. Now, a random sample of 50 hours is used to determine this average. If the standard deviation is known to be, how about 3.8? I'm just making this up. Determine the 90, we'll use 99% confidence interval of the mean mu. Okay, so we're a hospital and we see patients come in and out and we start collecting data. And on average, we say there are 22 patients an hour. Now, how did we obtain this average? We obtained this average by taking 50 hours. So we sampled every possible hour. We took 50. So what we'd like to know, how confident are we that sampling only 50 hours gives us a true sort of estimate of the actual mean? So when we do this problem, I think it might make your point a little more clear, but we'll find out. So here we go. For 99% confident interval, here's what we use. So before we do anything, let's note the important sort of variables in this problem. So n is 50. X bar is 22. And of course, sigma, I said what? 3.8. What else do we need? Well, we also need z sub alpha over 2. So for the 99%, we take the number 2.58. How did I get 2.58? Well, we showed you how to figure it out for 95, but if we did the similar reasoning for 99%, Z alpha over 2 is 2.58. So really all it becomes now is a plug and chug. And so sometimes it's helpful to do some of these computations beforehand. So what is Z sub alpha over 2 times sigma over the square root of n? Well, that's 2.58 times 3.8 over the square root of 50. And so we can go to a calculator to get that. I'll use one on my phone. I think I will. Yeah, I will. So, and by the way, some people always say like when they teach, they like to have the calculations done beforehand, but I think that's silly because that gives you the false sort of perception that these things can be done in your head or that they can be done quickly. And really what you should be doing is taking your time. So if I go to a calculator and I plug these things in, I have 2.58 and that's times 3.8 divided by the square root of 50. And barring I know how to use a calculator, or assuming I know how to use a calculator, we get 1.38, we'll round 1.37. So hopefully you guys get the same number, and I hope that you'll actually do it yourself. Okay, so the confidence interval from the previous page or pages so remember it's x bar minus Z sub alpha over 2 times sigma square root of n, and that's less than the actual mean, which is less than x bar plus this scary creature. But we know what these numbers are. This is x bar is 22, and then this is plus 1.37. And then this is 22 minus 1.37. And now it's a calculator problem. I'm sorry, why did I rounded that up? This is 1.39. I did that wrong. I'm sorry, 1.39. If I round the 2 decimal points, it's 1.39. So this becomes 23.39. And then if you subtract this thing from 22, you might not be able to do that in your head. You get 20.61. All right, so all this math, what does it mean? Before we write down in English what we have happening here, let's take a moment. If you have a comment or a question, please let me know.
Could you go back to the previous slide just real quick?
Yeah, sure.
Thank you.
Yep.
Okay, I'm good.
So what does this mean? How do we interpret this? If we translate this from math to English, what does the translation mean? Well, here's one way to think about it. So if we translate it as we can be 99% confident that mu is between these two numbers. We're not 100% confident, but we're 99% confident. Now, what I'd like to do is, and I know we're running short on time, but to go back to sort of your point about why not just do, let's see what happens if we do a different interval. Instead of doing 99, what happens if we do 90? We'll see how this changes. Does anybody have a comment or a question? What do you mean, Sam? I'm not quite sure what you're asking, Marshall. Like one of the ones we did from the homework, you mean? If you're talking about that, yeah, we can do that. Yeah, we can do that in a second. Let's just finish this because I think it'll put a bow on this if we change sort of our size, or excuse me, our confidence interval. So for comparison, let's do a 90% interval. And I'll go a little quicker this time. So if it's 90%, you have mu less than 22 plus. Now, what was the number for 90%? For 90%, our z alpha over 2 would be 1.65. And then, of course, this is times 3.8 over the square root of 50. And then over here, you have 22 minus 1.65. I guess I'll use parentheses here. And this is 3.8 over the square root of 50. So if we just do the calculations, maybe you go back to your calculator and 1.65. So if I do this, this becomes 21.11 less than mu and less than, if I do adding, 22.89. So what you'll notice is the interval has now shrunk. It's shrunk. It's smaller now. So even though, so I gave up less confidence, now I'm only 90% sure that it's this close. So when I want a better estimate, I give up confidence and vice versa. So hopefully you'll think about that and how it could affect or how it sort of goes with your question. All right. Does anybody have a comment or question about this? All right. So I think, Marshall, you asked about a homework problem. Do you have a particular problem that you were asking about? So you want like a sample mean probability problem? We can definitely do that. All right, so okay, let's see if we can get one here.
Quick though, my internet kind of lagged out whenever you were explaining it, but I wrote it all down now. So how did you get the 1.65 then? Was that from the
This is
chart?
for 90% interval. you use, that's the Z sub alpha over 2. So for when you want 90%, it's 1.65.
So those will always be like given to us though, in those kind of problems?
What do you mean given?
I guess I shouldn't have said given, but
Yeah,
I'm saying like,
given's a bad word. So the reason I gave you these are the 3 standards. So for example, someone who does this for a living has these things, you know, that knowing what these numbers are is no different than you knowing that 2 plus 2 is 4. But in general, if I said find the 96% confidence interval, you'd have to determine what these numbers are. Now, you know, the examples I've given you thus far, I've chosen one of these standard intervals. So, it's possible that I could ask you to determine a different one, but most examples in the book and most examples or problems that we ask you to do will tell you what number to use, whether it's 90, 95, 86. And then if it's a standard interval, you know what the number is. And if it's not, then you have to determine it. Does that make sense?
yeah, I'm just like still kind of just a little bit confused with it, just understanding like how to determine it then.
Well, right, but that's the hard part. So, I mean, that goes back, determining it goes back to our original problem. Our job is, if we want a 95% confidence interval, we say, okay, what area of the curve is 95%? Well, if there's 95% red, then that means there's 0.05, half of that here, and then the other half over here. Do you understand that part?
Yeah, I got that.
Right. So now your job is to go to the table, wherever it is, and figure out which value here, what number gives you 0.025. So what I do is I go to the table and I go to a table and I say, okay, I need 0.025. Well, this particular table tells me the gray area. So if I annotate this, to find when this is 0.025, I need to know, well, what's 1 minus 0.025? Do you understand what I'm saying here? So we need to now, if I want the 95% confidence interval, what I have to do is I have to go to my calculator and I say, okay, what is 1 minus 0.025? And that is, the gray area is then 0.975. Now, of course, you're going to say, well, why isn't it not 9.5? Well, don't forget, you're missing the other piece over here, which is also 0.025. So if I add 0.025 to 0.95, I get 0.975. So the gray area that I need is 0.975, which means I have to go down here on this table and I have to figure out, okay, which Z value is going to do that for me? Which Z value is going to get the job done? And I don't want to annotate. Why is it doing that? Give me a mouse. And so, okay, I go down here. I need to find 9.975 in my chart. So I come down here and I say, okay, where's 0.975? And then I see it. It's right here. So let me get these out of the way. I need to find 0.975, and here it is. Now, what Z value corresponds to? Well, the first 2 digits are 1.9, and then if I scroll up, I'll see that the second digit is 6. So I have 1.96, and that's how I get that number.
Okay, yeah, that made more
Come
sense
back
now.
down here, it's in the column of 0.06 and it's in the row of 1.9. So that is how we come up with the number 1.96. So again, this is, I hate saying this because it sounds like it's like a cop out, I guess, for me, but it's not. I mean, no bit of this can be learned in watching in an example. I mean, all we can do when we're in these sort of scenarios where we're having a Zoom or a lecture or a problem session is we can supplement it. But for most human beings, trying to learn this is a time-consuming sort of thing. It's very it's very unlikely that most humans can learn this in 10, 20 minutes. It has to be something that is, you know, it's something that you spend some time on. And I know you guys don't want to hear that. I know you got other things in life. But the fact of the matter is, you know, this stuff is not, you know, it's not easy to learn. I mean, you're learning a language and you're trying to interpret that language. You're learning the language of math and prob and stats, and you're trying to interpret it into English, and that's not always easy. And then, you know, so sometimes I think what happens is we get discouraged, and what you need to do is just remind yourself that it's natural to be confused. Anyhow, I don't know if that makes you feel any better or not. And I wish I could say, guys, go home tonight, and if you say this 3 times before you fall asleep, you'll wake up and it's easy and it all makes sense. But that's just not how it works. I mean, look, I can show you this. I got all kinds of books over there. Oh, it's all you read, and it takes lots and lots of time of reading lots of different things before you learn things. It's not an overnight thing. Learning is a process. It is not like a light switch. So, unfortunately, it would be nice if it was. Okay. Let's do a problem about sample means. So we will leave the world of confidence intervals for a second. So Marshall wanted to know about a sample mean problem. By the way, I know class is over, so if you guys got to go, feel free to go. I won't be upset, but if you want to stick around and see how this problem is solved, here we go. Okay, so research shows that how about the starting salary for job blah, I don't know, in, let's pick a state. How about Pennsylvania? In Pennsylvania is on average $52,000 per year. I don't know. I don't want to pick a job because I don't want to insult jobs or make other jobs seem better. But let's call it job blah. In Pennsylvania is on average $52,000 a year. So let's assume salaries so if you assume that the salaries are normally distributed, with, let's say, standard deviation, how about 4,250? So, and by the way, you might say, well, why would we assume that it's normal? Well, I mean, again, this is sort of inferred. Perhaps we collect our data, we do our research, and we visualize it, and it looks like a bell curve. So it's not wrong for us at that point to assume that it's normally distributed. So let's determine 2 things. 1, let's determine probability, a randomly selected person makes more than, let's say, 55,000. And then if 75 people are selected, determine the probability that X, the sample mean, is, say, greater than or equal to 55,000. So let me rewrite this, because this is scary. Say selected. That was some scary penmanship. So Marshall, this is a good problem. I hope that before we even solve it, let's look at the distinction between the two things it's asking. The first part is asking you about a person, one data point, just one person. The second part is saying, let's choose 75 of them. Now we're asking about the average of those 75. What can we say about it? So the most important thing in this problem is to understand that there is a distinction on how you're handling this problem. The first part will be solved one way. The second part will be solved a different way. Does anybody have a question about that? All right, so let's solve it. So the first one, we have a couple options. So what is the probability that a randomly selected person makes more than 55K? Well, one way to think about that is to just go plug it into a calculator. So last week we did this. We said there's two ways to do this. There's the old-fashioned long way where you transform this particular probability to z-value and go look it up in the table, or you go to a calculator. So if I go to a calculator, one way to do that is I can literally just go to normal calculator. And here's the first hit. Do we want to use this one? We could. Oh, and look, here, this one is actually fits our bill because this one is telling us the shaded area. All we have to do is plug in our numbers. What was our mean? Well, if I go back to the problem, my mean was $52,000 a year, and my standard deviation was 4250. So my mean is 55,000, or no, 52,000.
And then you get the screen share with us.
You're not seeing it?
No.
No, you're not. I'm sorry. Anyhow, so all I did was Google normal calculator, and this is the one that came up. And if I plug in my numbers and I want to know what's above 5,500, there I go. It does it for me. It did the work for me. I didn't have to do anything. So again, I plugged in my mean, I plugged in my standard deviation, and then I wanted to know when it was above 5,500, and it comes back with the area, the probability under this curve to the right, which is what I was after, right? If I go back to the problem, I asked that a randomly selected person makes more than 55,000. So that's what I asked to do, or I asked the computer to calculate for me. I asked, hit the wrong button. That's not what I wanted. You don't care about that. I asked it to tell me when it's above 5,500, and it did, and it's 0.4719.
Wouldn't you also have to terminate the 0 on the 4250?
Say
Since
that
you're getting
again?
rid of a 0 on the 55,000?
What do you mean? Oh, no. Yeah, you're right. I have a typo here. You mean because I didn't put enough zeros in?
Yeah.
Yeah.
So then I guess the standard deviation.
Yeah, so
would
that's
go
right.
up.
So that was we're gonna have a slight. We want to know when it's above 55,000, right? So that's a typo. So the answer is 0.24. Good observation. Does that make sense now? That's my mistake. So the point was I didn't have enough zeros here. I put 5,200 instead of 52,000. I think we're good now. So the answer is 0.24. So the probability then that a randomly selected person makes over $55,000 a year is 0.24 or 24%. So you can do, when you're asking about a single data point or one point of it, then you're fine. It's literally you go to a calculator if you want, or you can do it the long way. I don't care. Some people might, I don't. Now, there's no shortcut for the second part because the second part is asking about a sample mean. And so in order to answer this, we have to use the appropriate formula given to us by the central limit theorem. So since this one is about means, we need the central limit theorem and the formula. So we need this z is equal to x bar minus mu over sigma divided by the square root of n thing. We need this formula. So in this particular problem, we know what these values are. They're given to us. Our sample mean we're interested in is we want to know when it's more than 55,000, and then that's minus 52,000. That's all over our standard deviation, which was 4250. And that's divided by the square root of how many people did I sample? Well, we sampled 75. So the z that we need here, we have to go to a calculator, I'm assuming. I don't know how many of you are going to do this in your head. But maybe you can. I don't know. So I'm going to go to a calculator and do it. So what is that? That's 3,000 divided by that. I got the wrong number. So if I go to my calculator and put it in, so 55 minus 52 is, so that's 3,000 over 4250 square root of 75, which becomes 6.11. So we know here's what we know. We know the probability that X bar is greater than 55,000 is the same thing as the probability that Z is greater than or equal to 6.11. So if we go back to our calculator, we can compute this. So since we're already in Z, we can use 0 and then standard deviation is 1. And we want to know when it's above 6.11. And you'll notice when we answer that, we get 0. And what if, just for fun, what if you did below? Now you get, it's going to spit out 1. So for all intents and purposes, I shouldn't say for all intents, this gets into some technical jargon. But what we found is this thing is equal to 0. So if we go back to the phrase of this, and we select 50 or 75 people, the probability is 0 that if we average them all up, their average is greater than 55,000. Now you should think about if that's realistic or not. Particularly in the scope of the average and the standard deviation. Now the answers the problems we did last week, we didn't have this interesting fact, but it is possible that this happens. It's possible the probability is 0. Does anybody have a question about this? Comment?
Thank you for going over that.
Does that make sense?
Yeah, I'm caught up now. I was just a little
Yeah, okay.
confused on the formula for the second part.
Yeah, and so here's an interesting thing. A good way to think about this is look at our standard deviation. Our standard deviation is 4,250. So that means the variance would be like 16,000 something. So, I mean, think about where most of the salaries would be. So this is an look, I just made these numbers up off the top of my head. I didn't really like go find a research study. But one way to think about this, though, is how is this realistic, or did we make an error? So this is a good example, I think, for you guys to analyze if you're trying to learn this. But well, listen, guys, I got to go because I have a 2 o'clock that I am past. So I would encourage you to think about this problem and the other stuff we did today. And if you have questions, please contact me. Do not forget that next week during finals week, I'll be available most days for questions and answers. And if you need to Zoom or whatever you want to do, you just shoot my email up and let me know. All right. Anyhow, I hope you got something out of this semester. I feel bad that it wasn't a normal semester, but you know, we'll make the best of it, and hopefully you had some enjoyment out of this. So I will see you guys. Well, I don't know when I'll see you again, but thank you very much. And please let me know if you have any comments or questions, and have a good holiday.
Thank you.
Thank you for everything.
Thanks,
Have a
O'Grady.
good-
Guys, have
A
a
holiday
good one.
Christmas.
Good luck on your exams too. I know.
Thank you.
Thank you.
but
Thank you.
Thank you guys. Appreciate it. Bye.
Oh, yeah.